Hi, and welcome to 4.6 Normal Force. In this lesson, students will be able to calculate the normal force acting on an object. So here's a little critical thinking for you, and there's going to be plenty of them in this lesson. If a 100 Newton sled is at rest, that means the net force is 0 newtons. It's in equilibrium, and Newton's first law is at play. Draw a free body diagram for this sled. So pause the video and draw a free body diagram. Your free body diagram might have looked like this. So hopefully you drew the box with the dot and you have a force due to gravity. Is that the only force that's acting on this sled right now? If that was true, this looks pretty unbalanced to me. There's nothing opposing that force. And therefore, you would think that it would accelerate because F is equal to ma, and that weight is equal to the force. So there must be something else going on because this sled is not accelerating down through the earth. So what's happening here is that there's actually an upward force from the ground itself, the normal force, okay? But don't overthink this too much. It's basically just supporting the sled. Um, there's something in the way from the sled. If you held the sled above the ground and then let it go, it would accelerate downward until it hit the ground, and then the ground would be there to stop it with its normal force. So what exactly is a normal force? The normal force, and we use F sub n, again a capital N, but this isn't for newtons, it's for normal. The normal force acts on a surface in a direction perpendicular to the surface. Actually, in physics, the word normal means perpendicular because physicists are not normal and they don't really know what that means. No, I'm just kidding. So normal is another way to say perpendicular though, so you'll have to remember that. And actually, when we do unit 15, which has to do with electromagnetic waves, we talk about refraction. And there's something called a normal line. And that line is perpendicular to the media interface. But it just basically means perpendicular, so we'll get there when we get there. The units for normal force, well, it's a force, so the units are in newtons, and that's a convenient thing. We're going to be learning about a frictional force, a gravitational force, a normal force. If it's a force, the units are the same, newtons. Now, there's multiple different types of forces that you could have, but the units are conveniently always newtons. So the formula, a lot of times people just like to know, okay, Mr. Nangle, tell me what the formula is. We learned that the weight is equal to mg, Fg equals mg, and then we're going to even have a formula for the frictional force in unit 5. We'll learn a formula for that frictional force. But the normal force doesn't get its own formula. The closest thing you could do is make your like net force equation and analyze the forces, but that net force equation is different depending on the situation. You have to draw your free body diagram and make your net force equation accordingly. So it's different every time. The formula, it says many times the normal force is equal to the weight, but not always. So when would the normal force not be equal to the weight? Pause the video and think about it. So let's do an example. It says a book with a mass of 5 kilograms is at rest on a horizontal table. What is the normal force acting on the book? This is very similar to that sled critical thinking we just did. So now we have a number and we could actually calculate it. So this is pretty straightforward. We have a book. That's our free body diagram for the book. And they show two forces acting on the book. All right, so the weight, Fg, and we have a normal force, F sub n, okay? So at this point you could do an analysis. Well, you could write the formula. If you wanted to be very thorough, you could write that net force formula that we talked about. So we would say Fn minus Fg. All right, and then what do we know about the net force on this book? Well, this book is at rest, so that means that it must be in equilibrium. So the net force is equal to 0. And we don't know the normal force, but we know that Fg is equal to mg. So we could continue plugging in numbers. Fn minus 5 kilograms times negative 9.8 meters per second squared. So this turns into 0 is equal to Fn minus negative 49. And now we're running into a problem here, right? Because we're going to get a negative number for the normal force when because this really turns into plus positive, and then we would get Fn is equal to minus 49. But the normal force is pointing up. How did we get a negative number? Well, I made a mistake on purpose here. All right, so let's back up. Since I wrote the net force equation like this, instead of like this, really it's the sum of the forces, so you should just add them all together. And if you add them all, if you're adding everything, then you could plug in the minus sign where it's supposed to be. Like we're saying, okay, gravity is acting downward, and that's where the negative comes from. If you decided to do it the way we originally did it, where we are subtracting them because we know we drew a free body diagram and we know that Fg is acting downward. So we're like, okay, we're subtracting Fg from Fn. You know, you could do it that way, but then just remember that you already took that direction into account and you don't have to, and actually you shouldn't make the 9.8 negative. Because then it like there's a double negative and ends up going in the opposite direction. So you just have to be careful on how you do it. I always kind of used to add them together and then make it negative when I plug it in because I remember that 9.8 should be negative. But you know, there are some situations where you want to look at your free body diagram and take that direction into account. So I just wanted to say that because I'll do it one way or another as we do more problems in the future. And I know a lot of people have a question about the direction of these things and when to make it positive and negative. So the normal force is equal to positive 49. You're going to add that 49 to both sides. And now we can see that the normal force is equal to the weight in this situation because they're totally balancing each other out. But the normal force doesn't always have to be equal to the weight. So I want you to try these on your own. It says calculate the normal force in each of the following situations. You may be surprised to find that the normal force is not always equal to the weight. Number one is very similar to what we did. Actually, I think it's the same. Yep, it's the same problem. But now we're going to do pushing down, pulling up, and then accelerating and moving in a constant in an elevator, and then on a hill. So there are these questions, and I'm actually going to like talk about how to do these in the next slide. So there is going to be a slide on this one, a slide on the elevators, and then we'll actually find the normal force for an inclined plane on a hill. But if you want some extra practice, you could do these, and there's actually going to be a video posted that talks about each one of these specifically. But let's continue on talking about normal force. So when would the normal force not be equal to the weight? If you have your book on the table and you are squeezing the book into the table, we're going to push down on the book. The book still isn't going anywhere, right? It's still at rest. You have an additional applied force on it, but the net force is still 0. So we didn't change the net force, but we have an additional force. So what does that mean? The normal force must have changed in order to have the net force still be 0. This is what the free body diagram would look like if it's just at rest. And then we apply a force. FA stands for applied force. Now we have more force pointing downward than we do pointing upward. And if the normal force stayed like this, then we would start accelerating downward because the net force is down. what happens when you push down on that book is you're squeezing the surfaces together more, and the normal force increases. And in this case, you could see the normal force is greater than, it's larger than the weight is. It was equal, but now the normal force changed and it's greater. And you could make your net force equation, and then you could also like rearrange it to say that the normal force is equal to Fg plus Fa together. They're equal to each other because the net force is 0. And you could see that the normal force is greater than the weight. Well, what happens if you are pulling up a little bit on the book? All right, so the book's at rest on the table, and you're basically like helping the table out by supporting the book along with the table. You're not lifting up the book. The book is still at rest on the table, okay? But you're pulling up slightly on it. So again, this is the normal situation where the normal force is equal to the weight. And remember, normal means perpendicular to the surface. See if the surface is here, perpendicular. Then you slightly pull up. You're helping the normal force out. Well, in order to stay at rest, the normal force must decrease because we want the normal force plus your applied force to be exactly equal to the weight in order to have the net force still be 0. And if the net force is 0, we can make this equation, Fg is equal to Fa plus Fn together. And you could see from the diagram and from this equation that the normal force is going to be less than the weight in this situation. Well, what if there's like a rope attached to the book and you pull it upward at an angle? What's going to happen to your normal force? What do you think? Well, if it's a frictionless surface, you'll definitely be pulled to the right because in the x direction, we have this x component of your applied force, and there's no force opposing that pulling because there's no friction in this case. So they're gonna have a net force to the right. But in the vertical direction, what happens is if the book is still at rest on the table vertically, but it's moving horizontally, you're not lifting up the book, you're just sliding it along, then the normal force decreases just like it did before. You're still, a part of your force is pulling upward. So it's very similar to that previous example, and you just look at the y component that's doing the work, and the normal force is again less than the weight. Very interesting. So, continued some more. Now you're thinking about an elevator. So if you've been in an elevator before, you know it moves upward and downward. Most of the time, the elevator is moving with a constant velocity. But if you're starting at rest and then you start moving up, that means your initial velocity was 0, and then you do have some upward velocity. So you must have accelerated at some point. Once you accelerate, then you start moving at a constant velocity for most of the trip until you decelerate again for a short amount of time. So let's say we're accelerating upward. What does that mean in terms of your net force? If you're accelerating upward, what do you know about your net force? Your net force must be upward as well. So if we were going to draw a free body diagram for this, we have our weight, which is, we'll make that the same for all of these situations. If you're accelerating upward, that means your normal force must be greater than your weight because you want your net force, which you add them together, to be up, to be positive. So this one is winning right now. What happens if you're accelerating downward? Well, our free body diagram is definitely going to change. If we're accelerating downward, that means our net force must be pointing down. And that means that the normal force must be less than your weight. The weight is winning now. So the ground gives out from you a little bit and you start accelerating downward. All right, so the normal force is less than the weight. Now, if you're moving at a constant speed, either up or down, what do we know? If it's a constant speed, it's a constant velocity, and you're not accelerating. So that means your net force is equal to 0 newtons, not on. It looks like on when I write it like that, but 0 newtons. And if the net force, the sum of these two forces is equal to 0, they must be exactly canceling each other out. I try to draw that equal sized. Okay, because remember, a force is a vector, and we're talking magnitude and direction. So you can use your free body diagram and try to draw it somewhat to scale to help you think about the magnitude and direction of these things. So yeah, the normal force is equal to the weight if you're moving at a constant speed because you're not accelerating and there is no net force. So here it is. This is the inclined plane. So right now you're hopefully sitting or standing on a plane. The floor is a plane, right? And hopefully it's not an inclined plane. An inclined plane is like a ramp, not a plane like an airplane. Sometimes people think airplane like an airplane. Plane like in geometry where you could have a point, a line, and then a plane, an infinite plane. So we think of these as infinite planes, but they're just really just ramps, something like that. Okay, so it looks like this, right? You have this nice diagram here. Now notice that the normal force, if I could draw a straight line here, the normal force is normal to the plane. It's perpendicular, makes a 90-degree angle to the plane. That is the definition of a normal force. It makes a 90-degree angle with the surface that it's contacting. Okay, so it's a 5 kilogram block on an inclined plane. This is 30 degrees. And what is the normal force? So it's actually the normal force is not going to be equal to the weight in this situation because part of the weight is opposing the normal force, but a component of the weight, let me try to make this component parallel to the surface here. A part of the weight, a component of the weight is parallel to the inclined plane, and only a part of that weight is acting perpendicular to the plane, not the whole weight, just a part of it, FG perpendicular. So the normal force is equal to this component. See how the two arrows are opposing each other? It's the block isn't flying off the hill or going through the hill. It might be sliding down the hill, okay, but in the perpendicular direction, the forces balance each other out. So the strategy is to find the perpendicular component of the weight. See how we have a nice right triangle here? Okay, so we know how to do the vector components. And once you know the perpendicular component of the weight, then you could figure out, you just set it equal to each other basically. The normal force is equal to that. So you could pause the video and try to do that on your own, or you can keep watching right now. So we're going to draw our free body diagram. We'll start by making our inclined plane, and we'll say this is 30 degrees. And then we draw our box. Now it's on an incline, it's at an angle, and I have trouble doing this. My strategy is to try to make the box perpendicular, perpendicular, parallel. And we try. Then you draw the dot like normal, and you draw the weight. The weight points straight down towards the center of the earth. Okay, this is FG. I don't know why that just erased. Okay, there we go. Then you have the normal force. The normal force acts perpendicular to the surface. So I'm going to draw a line that's trying to be perpendicular to that inclined plane, and I'm going to call that F sub n. Okay. Then here's the trick. You break the weight into parallel and perpendicular components, not x and y. You see, you could make an x and y, like if this was, okay, beautiful, very nice. And then look at that. That's right in line with the weight. And then you might say, well, why don't you just break the normal force into x and y components? Wouldn't that be easier? The strategy is to not use the x and y axis, because what we're going to do next in Unit 5 is learn about friction. And the frictional force acts parallel to the surface. And if we used our normal x and y components, then we would have to break this frictional force up as well. So then we got to do components here and components here, and that's just a lot of work. So if you're a savvy physicist, you take these x and y axes and you rotate them to align with the hill, the inclined plane. And the x-axis turns into what we call the parallel axis, and the y-axis turns into what we call the perpendicular axis. And now my free body diagram looks ridiculous, so I'm going to redo it. All right, so there we go. I didn't draw on the normal force yet because I want to focus specifically on breaking the weight up into its parallel and perpendicular components like we just talked about, okay? So the perpendicular component looks like this. You draw perpendicular to the surface, but where do you stop? Some people draw it like this, and then they're like, oh, nice, I got a right triangle right here. But look at this arrow. Is this arrow parallel to your surface? No, it's not parallel to the surface. So this is too long. We want a parallel component of the weight. So this is what tells you where to stop when you're drawing your perpendicular component. And the right angle of your triangle should be over here. Okay? So we'll name this FG perpendicular. That's the symbol for perpendicular. And we'll name this FG parallel. And a great person once told me that it's like the parallel looks like two skis, and you're skiing down the hill. See how you're skiing down the hill? So that's a way to remember which one's parallel and which one's perpendicular, okay? Then we got to do some work, okay? And this is where you might have gotten tripped up. The 30-degree angle here is right here, 30 degrees, okay? It takes a little bit of geometry to prove that. We don't have to. Well, you could just take it at face value if you want. You could try to prove it yourself, but just remember that this angle is equal to this angle right here. So if that's where you ran into some trouble, you could try to continue from here, break that weight into the components, okay? So we also know some information from the problem. We know the mass, all right? The mass of the block is 5 kilograms. We know we are on Earth, so that's negative 9.8 meters per second squared. And we know theta is equal to 30 degrees. So the strategy is to find the weight first. Fg is equal to mg. Fg is equal to 5 times negative 9.8. So you're being pulled straight downward towards the center of the Earth with negative 49 newtons. Okay, down. So now we have is this the opposite, adjacent, or hypotenuse of that triangle? It's the hypotenuse. And we have the hypotenuse, and here's your angle. What is the perpendicular component? The perpendicular component is adjacent. So we have adjacent and hypotenuse, and we could use the cosine. So FG perpendicular is equal to FG cosine theta. That's how you write that. That's going to come up again and again. So this is like the first part, and this is the second part. So FG, the perpendicular component of the weight, is equal to the weight times the cosine of the angle. So the perpendicular component of the weight is equal to 42.4 newtons. So not all of the weight, just a part of it. Not 49, but only 42.4. Let me rewrite that. Now we are ready to find the normal force, because the perpendicular component of the weight is what is balancing out the normal force. These two forces are in equilibrium, and I know that because the block is not accelerating through the hill and it's not accelerating off the hill. It might be accelerating down the hill, which is caused by this component of the weight. But we know that these two are equal to each other. And we could we could write a net force equation to prove that. And by the way, after you do a bunch of these, instead of like separately doing the weight first, you could actually plug in Fg equals mg right over here instead. So you know the shortcut, but then you also know the weight is equal to mg. And now this is like the shortcut for inclined plane. But anyway, let's make that net force equation for the perpendicular direction. Actually, let's erase the given information too, just to clean it up a little bit. So the net force, oh my God. So we could write the net force in the perpendicular direction is equal to the normal force plus the weight in the perpendicular direction, Fg perpendicular. And I decided to do plus this time as opposed to making it minus, because I know that they're in opposing directions, but I'm just going to remember that I'll show that opposing direction by making this negative when I plug it in my equation. So let's think about what we know now. The block, again, I said this before, is not accelerating in the perpendicular direction. It's accelerating down the hill, but not in the perpendicular direction. Therefore, since there's no acceleration, there is no net force in that direction. The normal force is what we're solving for, and the weight, the perpendicular component of the weight, is 42.4 newtons in the opposite direction. So we'll make that negative 42.4 newtons. To solve, you just add that to the other side, and you get a normal force of 42.4 newtons. They cancel each other out. They're on opposite sides. Okay, so that's nice. We found the normal force, and as you can see, the normal force is less than the actual weight. So this is the perpendicular component of the weight, but this is the weight, this is the force that gravity is exerting on that block. All right, so the normal force is not equal to the weight here. It's not always going to be equal to the weight, and that's okay. Part B is interesting. It says, what is the acceleration of the block? We said it's accelerating down the hill in the parallel direction. Well, in the parallel direction, there's only this one force. There's no other force acting parallel to the hill yet. When we do friction, then we can add in a frictional force here, and we'll have to take that into account because this and this are both parallel. But for now, we'll just figure out what the parallel component of the weight is. So if we wanted to do the shortcut method, we could say FG parallel is equal to FG, and then see how this is the angle and this is opposite. So we have opposite and we have the hypotenuse. So it's FG, opposite and hypotenuse, sine theta. Okay. And there's another. So remember how I said, oh, these are like skis? Well, this S is like you're skiing down the hill. And if you ever skied down the hill before, you go shoo, 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 down the hill back and forth. So for those of you who've gone skiing or snowboarding down a hill, you recognize this motion. And that's kind of a way to remember, oh, if it's going down the hill parallel, I use the sine. All right, so this is cosine, this is sine. But anyway, let's continue making our equation. So FG parallel is equal to, FG is equal to mg sine theta. And now we could plug in our numbers. And now we solve and we get FG, the parallel component of Fg is equal to only 24.5 newtons. So of this 49 newtons, there's only a component parallel to the hill, and it's exerting a force 24.5 newtons. That's because 30 degrees is not that steep of an angle. It's actually not really to scale, I don't think, here. So yeah, this component's going to be greater than this component because of the angle of the hill. If it was a steeper hill, then this would be greater. So let's write that in. And we'll use that force in our net force equation. So now we could write, well, the net force in the I was going to say in the y direction, in the parallel direction is equal to how many forces are acting in the parallel direction? Only FG parallel, okay? But what do we know about the parallel direction now? Is it in equilibrium? Well, if this is truly the only force acting on that block and there's no friction, we know that it's not in equilibrium. And if it's not in equilibrium, this force isn't balanced out by anything else. Therefore, the net force isn't zero, it's equal to m times a. So you could do that instead. So this will either turn into 0 or ma because of Newton's second law if the forces are unbalanced. So ma is equal to, and then I'm just going to call it 24.5. I'll get rid of the red ink to keep it simpler, okay? And actually, before we plug in numbers, let's make a nice equation here. Okay, so now we know the mass of the block, 5 kilograms, times A is equal to 24.5 newtons. And to solve for the acceleration, you just divide and you get 4.9 meters per second squared. So it's accelerating downward at it's getting faster, 4.9 meters per second every second, which is, pretty good acceleration because this is the only force acting on it, and that's a pretty substantial force. Anyway, this video is now 32 minutes long, but that was so much fun. Isn't inclined planes? That's really cool stuff, right? It gets even cooler. That's about it. Thanks for watching and have a great day.